Matrix determinant properties. I'm going to cover basic properties of determinant. But before I start, I just would like to remind you what's the difference between the concepts of matrix and determinant. Matrix is a table of elements, while determinant is a number. Okay? So let's start. There are about 10 properties of the determinant, but only some of them are of real practical importance. So let's look into a few of them. So first one. When a matrix is transposed, the value of its determinant does not change. That's a property number one. When a matrix is transposed, the value of its determinant does not change. So let's see. We need to transpose the matrix. We have matrix A is equal 1, negative 2, 3, 4, 0, 6, negative 7, 8, and 9. Okay, determinant of this one is 1, negative 2, 3, 4, 0, 6, negative 7, 8, 9. I'm not going to show the process. It's equal to 104. If you are interested, you can look at the video determinant, how to find determinant of matrix. Okay, excuse me. So let's transpose this matrix. Transpose, so which means the column I am making as a row. It's first column I am writing as a row. 1, 4, 7, 2, 0, 8, and 3, 6, 9. Practically all rows I wrote down as a column. So let's find the determinant for that one. One, 4, 7, 2, 0, 8, 3, 6, 9. And if you do find the determinant, you will see it still will be 204. So you can find determinant on your own and confirm that it doesn't change. It's the same. So as a result of transposition, the first row became the first column, the second row became second column, and the third row became the third column. Rows became columns and the result did not change, from which it follows important fact. The rows and columns of determinant are equal. In other words, if some property is true for a row, then the same property is true for a column. It's very important to know. Okay, so for example, you have, let's say, matrix in a row, yeah? Let's say you have some number matrix in a row. If you don't like to deal with matrix in a row, especially when you do multiplication, maybe it's easier to have it in the format of column, then you can write down in the form of column, right? This property itself is not much practical, meaning that we don't use much in practice, but it's helpful in understanding some problems in higher mathematics. For example, we can use this property when we examine vectors for coplanarity. Their coordinate can be written both in the row of the determinant and in the column. So this is for property for higher mathematics. Okay. Moving to next property, number 2. Next property says that if 2 rows or 2 columns of the determinant are swapped, then the determinant will change the sign. If 2 rows of the determinant or 2 columns, as a matter of fact, are swapped, then determinant will change the sign. Now, you need to remember here one thing. We are talking only about determinant. Nothing can be rearranged in the matrix itself. Okay? So let's play now a kind of Rubik's Cube with determinant. Let's say we have 1, -2, 3, same matrix, 4, 0, 6, and -7, 8, and 9. And determinant, we know, is equal to 204. Okay, so what I'm going to do, I'm going to swap first and third rows. R1 swapping with R3. And we are getting -7, 8, 9, 4, 0, 6, 1, -2, and 3. How much is going to be determinant? -204. So we swap 2 rows, first and third one, and we got negative sign. Let's swap again. Now this time we're going to swap second and third one. Okay, from here. From what we have, determinant -204, we're going to swap second and third one. Okay, and we are getting -7, 8, and 9, 1, -2 and 3, 4, 0, and 6. Let me move it closer. Okay, and if you calculate determinant, we are going to get positive 204. Let's do one more time. Swap, well, we did already, second and third one. Let's swap again. The second and third column this time. Column C, second and third. And we are getting -7, 1, and 4. We are getting 9, 3, and 6, and 8, -2, and 0. And guess what? We get -204. Okay? So that means that if we swap any pair of rows or columns, it change the sign of determinant to opposite. Now, this property, where we can use, where it's useful, it is useful in the cases where, let's say, we have negative sign in front when matrix is negative and we need to find determinant. For example, we have negative sign 2, 5, 7, 3, 4, 6, 9, 1, 6. Okay, and I'm going to find the determinant. So this is going to be this negative I leave in front and then put in parentheses 2 times 4, 6, 1, 8. Remember, real quick to refresh your memory, we are getting, let me see, the first line and first column, which is these 2, and multiplying by determinant of this one. Okay? Next, it's going to be minus. Now, second one, second column, first row, which is going to be 5, multiplying by, what do we have? This matrix, 3, 9, 6, 6. So, negative 5, it's going to be 3, 9, 6, 6. Okay, and then plus, same way, here we have 7, now first column, first row, and we're gonna multiply by determinant of this 2 by 2 matrix, square matrix. By the way, to remind you, we can find determinant only for square matrix, right? So here I have 3, 4, 9, 1, and closing parentheses, and then we open parentheses, flip the sign, so it's going to be negative 2, 4, 6, 1, 8, plus 5, 3, 6, 9, 6, minus 7, 3, 4, 9, 1. Okay, I'm not going to calculate this. It's easy if you can calculate yourself, or if you don't know, go back to the video about determinant. Now, my point is, instead of going through all this trouble, what we can do, we can swap. Remember, we just learned the property. We can swap 2 rows or 2 columns and get rid of negative number, because it will flip the sign of determinant, right? So, which means 2, 5, 7, 3, 4, 6, 9, 1, 6 with negative sign. It's going to be equal. I'm going to swap 2 rows or any 2 columns. So first row and second row. I'm going to swap first row and second row, which is going to be 3, 4, 6, 2, 5, 7, 9, 1, 6. And I'm going to get it positive. I'll put specifically positive so you can see. And you can see, I don't have to put in negative sign in front of any parentheses. Just solve it without dealing with negative sign. Okay? So this property also helps to better understand, for example, some properties of vector, the product of vectors or mixed product of vectors. It helps. But why does it help in the topic of vectors? Because vector we can represent as a matrix. Okay? All right. Property number 3. Let me make thicker the previous properties also, so it will be more expressive. And this one also. Okay. Property number 3. From the row or column of the determinant, you can take out common factor. One more time. From the row or column of the determinant, you can take out common factor. Here you have to be very careful. This rule is about one row or one column only in the determinant. Do not confuse with matrices where we are taking out a multiplier, okay? So where all the, from all numbers we are taking out common factor. In this case, we are taking out from common factor only from one row or one column. So let's work on it. So what do we have? Let's assume we have matrix or determinant of matrix, -1, -4, -6, 5, -4, -7, 2, 8, and 3. Wow, too many minuses, right? So we are going to use this property, get rid of this negative signs. So what we are going to do, we are going to take out -1 from the first row, okay? And we are going to get equal, taking negative here, and we get +1, 4, 6, 5, -4, -7, 2, 8, 3. So we took negative sign out and we got this type of determinant. Now, I don't like the second line also. See, I have there 2 negatives. I want to get rid of these 2 negatives also, which means if I take one more negative, this negative will become positive, right? So let me write down this negative times by another negative, correct? Which is going to give me positive. I'm cleaning this and writing down this is equal 1, 4, 5, 1, 4, 6, I'm sorry, -5, 4, 7, 2, 8, 3. And the determinant is coming out positive in front of determinant. It's going to be positive, right? All right. So from here, what else we can do? I'm looking at all numbers in the second column are divisible or dividable by 4 without any remainder. Well, let's do that also. And this is going to be, now I'm going to divide the second column. See, I have 4, 4, 8. So I can divide, reduce by 4. So let's see. And we are going to get 1, 4, 6. Actually, I'm sorry. We are dividing 1, 1, 6, negative 5, 1, 7, right? Dividing by 4, and 2, 2, 3. Okay, let me create space for this 4 that I took out, common factor. And I'll put here 4, right? Okay. So, what did we get? Our original matrix, we changed to this form. Now, if you're wondering if the determinant is going to be the same, well, let me answer on this question. Negative 1, negative 4, negative 6, 5, negative 4, negative 7, 2, 8, 3 is equal 4, 1, 1, 1, 6, negative 5, 1, 7, 2, 2, 3, and this is equal negative 216. Now, if you wonder why we have negative, it's determinant, we can get positive, negative, but to deal with entire matrix with negative signs, it's easy to slip and make mistakes, and with positive it's always easier to work with, right? Especially when numbers are greater, big numbers rather saying. So this is the property that is very helpful. Okay, in practice, the introduction of a minus often performed. So let's see, if we consider negative sign, for example, negative, and I have 6 to 1 to negative 1, and I have negative 2, negative 3, 8, 2, 1, negative 3, right? Well, I can change and get 6, 2, 1, 2, negative 3, negative 8, okay, and 2, 1, 3. What did I change in this case? I got rid of, not on this one, on this one. So there are, got rid of negative sign in the column. It is also worth to note that numbers in the first column are divisible by 2, right? 6, 2, and 2. Here, 6, 2, and 2. And we can divide it by 2 without any remainder. But I'm not going to bother with it because the numbers are small, it's easy to work with them. So I'm going to leave it alone. It makes sense to divide if the multiplier is large enough, let's say 13, 17. For example, if we have, let's say, we need to calculate determinant for a matrix like 33, 55, negative 14, negative 21. Now, those are different stories. I would reduce definitely. I would jump to reduce. Okay? Okay. So, moving to the next property. If two rows or columns of the determinant are proportional, it's a special case, or they are the same, then this determinant is equal to 0. Okay, let's take example. 4, 2, negative 2, 2, 1, negative 1, 5, 7, 3. Okay, let's see. First and second rows, lines. Look. First one. And second one. If we divide the first column, first line by 2, we'll get the second one, right? So they are proportional. Or if we reduce, we can say they are the same. Therefore, determinant is equal 0. In this case, we have second. Let me see. 5, 7, 3. Yeah, okay, no. It is sometimes said that determinant strings are linearly dependent. Since the value of the determinant does not change during transposition, the linear dependence of the columns also follows from the linear dependence of the rows. Well, there is a kind of geometric meaning to that, and we use this again in the vectors, in the understanding of linearly dependent or independent vectors that we call coplanar. If you don't know this stuff, just take a note, because I'm going to cover. And once I cover, you will remember this video, and that will make sense to you. Okay, now, let me take another matrix, determinant of matrix. Negative 3, negative 1, negative 1, 3, 1, 1, and 6, 2, 2. What do we have? 3 columns are proportional. Look at that. All 3 columns are proportional. So if I reduce the first column, divide by how much? By 3, I will get the determinant of matrix where all 3 columns are equal, or in this case proportional, and hence determinant is gonna be 0. Okay, so these properties I mentioned, they are used in practice, but here is the thing. The converse, opposite direction, you can't say it's true, because if the determinant is equal to 0, it does not yet follow that its rows or columns are proportional. Okay? It's not true, the statement, vice versa statement. Okay? Therefore, the linear relationship of rows or columns may not be explicit. Okay, next one. Property number 5. Determinant with 0 row or column equal to 0 also. We have 0, 2, negative 1. We have 0, 3, 4, and we have 0, 4, 5. we have in this case, first column is all 0. Therefore, determinant is 0. Well, you can solve it. I can fly over and show you real quick, because it's going to be 0, 0, 0 everywhere, the multiplier. Let's see, 0 times 3, 4, 4, 5 minus 0 times 2, negative 1, 4, 5, and plus 0, 2, negative 1, 3, 4. We are getting 0 minus 0 plus 0 equal 0. Okay, these properties I covered, they are the ones that are useful to know. So those, one more time, the value of determinant does not change when transposed. Second one, if you switch the pair of rows or columns, it reverses the sign of determinant. Third one, it's from row or column of the determinant, you can take out multiplier or common factor. Okay, and the last one, if the rows or columns of determinant are proportional, then the determinant is equal 0. And also, if there is a row or column that filled out with 0, it also gives us determinant 0. Okay, I think this was useful information for you to know, and I'll see you in next video.